Okay, so we've been told that the number of patients admitted to hospital in a randomly chosen interval of 15 minutes can be modelled using a Poisson distribution with this particular parameter of 10. So remember, that parameter there is the expected rate of success. Okay, in this case, call it the mean, which it's absolutely fine to call. We need to find the probability that exactly 42 patients are admitted to hospital in a randomly chosen interval of 60 minutes instead. So if I say, first of all, that my random variable, so you remember when we're doing distributions, I always say to you, make sure you define your distribution, okay? So let x equal, in the last example, the number of goals scored, right? In this case, with Poisson, it's particularly important. The reason being is because for the first case, it's the number of patients admitted in an interval of 15 minutes, okay? So if I define, first of all, x, it's up to you how you want to define it, but I'm going to define x as the number of patients, but here's the crucial bit, it's the number of patients in 15 minutes. Okay, that's the crucial bit which I want to highlight. So when we're dealing with this particular distribution, so the parameter of 10 that we're given, we're told that x is distributed using a Poisson distribution with a mean of 10, right? So this is only true if we're dealing with an interval of 15 minutes. Now you remember that one of the assumptions of the Poisson distribution basically says that we have randomly chosen intervals, right? So basically the intervals are independent of each other, is the way which I put it. So in other words, if I look at 15 minutes, any 15-minute period I kind of look at, I expect to always get about 10 patients admitted, okay, regardless of when I'm looking at it. Which means, using that assumption, that if I want to look at the next distribution, or the next random variable, if you have a look, I need to look at an interval of 60 minutes, not 15. So in such an instance, what I'm going to have to do is redefine my random variable. And I'm going to say, okay, it's the number of patients admitted to hospital, this time not in 15, but in 60. Okay, so you notice that when you define your random variable for a Poisson distribution, it's really, really, really important that you define your time interval. Okay? So once we've defined this, we can think about what the distribution is going to look at. So y is going to be Poisson distributed. What's the parameter? Yeah. Absolutely, it's going to be 40, right? Because if you think about it, the connection between the intervals is just basically making an interval 4 times longer. Okay?
If I remember correctly, this is like the process of Poisson, right? It's lambda times t.
Okay, so what you're thinking about there, you're absolutely right. So it's a discrete space-time distribution, right? So yeah, you're absolutely right. If you want to make it more...
I mean, that's not the point of the class, but...
No, I completely agree. No, you're right. So yeah, absolutely. The reason why it's lambda times t is because you're taking the rate of success and you're timesing it by whatever your time interval is. Absolutely. Assuming, of course, that t is just 1 unit, right? So yeah, you're absolutely right. It's just lambda times t. And actually, if you are interested, the continuous case of the Poisson distribution is the exponential distribution. And if you think about the formula of that, it's not just got e to the negative lambda, it's got e to the negative lambda t in that formula, which is why this whole kind of process comes about. But yeah, for the moment, you don't have to worry about that. You can just simply look at the time intervals, see what the scale factor is, and then you can think about what that, what your parameter is.
If I have to, just start with my first line, a theoretical perspective, but I mean, I just...
Yes. Either way is fine.
If I put t in it, it's the factor between the initial...
Yes.
The initial time frame we have compared to the one we're looking for?
Exactly. Well, kind of, yeah, exactly. So it depends how you define lambda, it depends how you define t. Yeah. So if you define lambda as just for 1 unit, then it'll just be lambda times t, and then t is just whatever your time is. However, if you define it how you've defined it, which is it's the scale factor.
Well, I agree with t, I do it, as you said, it's just, we already have the lambda for that time period.
Yeah.
So
Yeah, exactly. Yeah. So either way, just multiply by 4 is the end result. Or of course, you could take this 10 divided by 15 just to get 1 unit, 1 minute, right? And then times it by 60, same thing. Yep. All right, good. Now, of course, we want the number of patients. This is our distribution done. We want to find the probability that exactly 42 arrive in 60 minutes. So we want to find the probability that the number of patients in 60 minutes, that's our y, is equal to exactly 42. So it's equal to 42. Now, before we go any further, I will just use a calculator in a second. Can anybody remember what the distribution, probability distribution function is going to look like for this?
So lambda k to e minus lambda over k factorial.
Yep, good. So the probability
Yeah, I have to learn this by heart.
x is equal to r
The undergrad
is equal to lambda to the power of r e to the negative lambda all divided by r factorial. You just use k instead, that's fine as well. Yeah, good. Of course, that formula is in the formula sheet, right? If you are interested in where this comes from, it's just basically thinking about the case of a binomial distribution, but just thinking about it on a bigger scale, because of course the difference between a Poisson distribution and a binomial distribution, they both follow the same kind of similar shape. It's both discrete. However, binomial has a fixed number of trials. Poisson kind of has as many trials as you like. It doesn't really have an upper limit on the number of trials. All right, good. So in other words, we just need to use this formula here. So we can say, okay, lambda, which in this case is 40, to the power of 42, times by e to the power of negative lambda, so negative 40, all divided by my 42 factorial. And again, just to illustrate, if you wanted to use GeoGebra, you can just change your distribution to be Poisson this time. You can change the rate of success, which is going to be to 40. And in this case, you just want equal to. So actually, it's nice and easy. You can just use the lower bound and upper bound exactly the same. Or you can just simply scroll down to the right-hand side, and you can find that 42 is going to be 0.0585. So it's about 6%, so 5.85%. Okay,